Hi, everyone. My name is Stephan Lavavej, and I work on the Visual C+ Libraries team, maintaining our standard template library implementation. And today, I'd like to talk about what we've done and where we're going from here. As we get started, yeah, you can add your questions in the chat, and I'll answer them at the end. Firebot will take care of collecting all of that. So this presentation is structured in three parts. First, we're going to have a very quick overview of what's happened in the last year since the last CPCon. Then part one will be covering about 5 CS+20 STL features. So this part is entirely standard. Even if you use another implementation, all of this will apply to you, and you'll be able to use it in your production code as soon as you can gain access to a version of your compiler and library that support all these features. There's one part where I talk about something that is specific to our implementation, but otherwise everything else is standard. And then in part two, I'll be talking about how we have developed all of these features with our contributors on GitHub. And this is so you can follow our progress and keep track of, okay, is this C++20 feature available yet? Or going forward, is this C++23 feature available yet? To understand our organization and our development process. So what has happened in the last year? Well, at CPCon 2019, we had a major announcement that we were open sourcing our STL implementation. So now all of the 3 major STLs are open source, and ours is what went from proprietary to open source, which is very unusual. We are licensed under the Apache License 2.0 with LVM exception, which is the same license that Clang's libcs+ uses. We chose that for compatibility deliberately. And in the last year, we've implemented about 50 CS+20 papers/features. It varies depending on how you count whether something's a top-level feature or not. I think it's about 50. And the majority of these are from external contributors on GitHub. And they've just been doing absolutely amazing work, really high quality. In many cases, they've been able to do things that were beyond our domain expertise. Particularly as C++20 has been adding more and more features that are highly domain specific, whether in multi-threading or math, things like that. And we have the STL maintainer team has extensively reviewed and tested these. So from the perspective of a user of MSVC, nothing has changed. They're still getting features faster than before at the usual level of quality, high level of quality. And the fact that it's open source is just an implementation detail. So in the last year, we've released, since we release VS updates about quarterly, we have had 3 full releases ready for production. And just at the beginning of this conference, CPCon 2020, we released preview 3 of the VS 2019 16.8 update, which will be available for production use in the near future. So it's really like 4 updates that have contained changes from GitHub. So we're still migrating our development process to GitHub. For example, the build system right now on GitHub is a new build system written from scratch using CMake and Ninja, which is awesome. And currently we build just one flavor, which is native desktop. We still need to port like CLR, one core, Spectre builds, all these other different flavors of the STL. We've migrated about 99% of our test suite to GitHub, but we still have a few lingering tests that we need to migrate over, and enabling test coverage of things like CLR. And we've been porting over bugs and other to-do enhancement issues from our internal databases with the help of our contributors. So our goal, and this is just a goal, it's not a promise, is that we want to complete the CS+20 STL features in calendar year 2020. We can't promise this because there's only a few months remaining in the year and we've got a number of large features to work through, but we're working really hard. We've got about 23 features left to do. So that'll be our focus for the rest of the year. And here is a quick preview of a graph. I'll be talking more about our status chart later. But this graph, the dark purple line, is the number of CS+20 features remaining to be implemented. It's gone up every time the committee has voted in features. It goes down whenever we commit a feature. And the little hover highlight there is the date where we announced last year that the S2 was being open source. So at that time, we had 60 top-level features to implement, and that has gone down to 23. And once it hits 0, we can declare success. So out of all these features, which ones will we be talking about today? I'd like to start off with one of the simpler ones. And for each of these features, I'm going to present a fully worked example, a little snippet, not just a snippet of code, but a small program that can just be directly compiled under std CS+ latest or CS+ 20, whatever your compiler option is. So what could be the simplest thing in the world we could look at? Well, what about like comparing integers? Integers are simple, right? They're not even like floating point. How hard could it be? So here is a program. To save space on the slide, I've minimized by making the font really small, the boilerplate like include and int main. But you can compile this and see what it prints out. So if I have a short whose value is -1, and if I have an int, an unsigned int, whose value is 1729, and I try to compare them with less than, what do I get? Like -1 is certainly less than 1729. Well, the fact that I'm asking this question, that I've highlighted this in ominous red, and the slide is titled "Usual Arithmetic Conversions," which, if you know what those are, that's highly ominous. This will probably lead you to think something's unexpected. Well, if you try to compile this, the first thing that it prints is a compiler warning. It'll say, "Whoa, unsigned, signed mismatch," or if you're using Clang, it'll say "comparison of integers of different signs." And these warnings are considered sufficiently dire that they'll be on at pretty normal levels of warning. So this is an indication that something weird is going to happen, and indeed, this is going to print false. So that's weird. Why is -1 not less than 1729? Well, the CS+ standards rules, which are inherited from C here, say that when you compare integers of different types, there are these conversions that happen, and they're usual as far as the standard is concerned, although they can definitely do decidedly unusual things. In this case, the standard looks at these and it says, that short, it's really tiny. Why don't we widen it? Why don't we make it the same type as the unsigned int? So you get that -1 as a short converted to unsigned int. And that is going to obey modular arithmetic. You're going to get the value of 2 to the 32 minus 1. And 4 billion is not less than 1729. So that's why false is being printed there. So this is definitely undesirable because if you're working with like a short, you probably don't want it to convert to an unsigned int whenever you compare it with an unsigned int. You just want a small type because, to save space or whatever. So you can write the correct code here, but you have to insert some cache. You have to think about the usual arithmetic conversions, which most programmers, can't name in detail because the rules are complicated. So CS+ 20 makes this a lot easier. There is a feature called integer comparison functions, and in the slide deck, when you can view the slides, they are all hyperlinks here. Our pull request 621 was implemented by our contributor Nirgi, and the integer comparison functions are provided in the header utility. So instead of using operator less than, if you call std comp less and pass it this short and this unsigned int, it returns the mathematical answer because -1 is indeed less than 1729. So this is templated and will do the comparisons and conversions necessary to get the answer that you would expect. So you'll get true there. And it will all, be inlined away in optimized mode because it's a relatively simple function. It's just there's a lot of template corner cases to handle. So you've got the full set of comparisons that you would expect, equal, not equal, less than, and so forth, in the utility header. And an additional one called inRange that will tell you whether a value of an input type can be expressed within the limits of an explicitly specified type. So that one's implemented with an interesting hybrid of compile time and runtime logic. There's a bonus slide at the end of the presentation when you view the slides that will quote our implementation and show you what that looks like. So all of those functions are const expert, but that's definitely not the only const expert stuff that's been added to CS+ 20. In fact, making things const expert has been an increasing theme in CS+ since const expert was added in CS+ 11. So when const expert was originally added to CS+ 11, it had very strong restrictions. You could only have like a single line return statement. So if you wanted to do any branching, you had to express it as a conditional ternary operator, which was excruciatingly terrible. And in the following standards, 14, 17, 20, const_expr has been repeatedly extended and strengthened both in the core language and the standard library, to the point where now it has almost all of the power of ordinary programming. There's still some things you can't do. You can't reinterpret cast, but a lot of the previous restrictions have gone away. And the library has been steadily adding const_expr to things. So here I tried to gather up all of the papers that we've implemented that have had something to do primarily with const_expr, but this is not an exhaustive list. Like those integer comparison functions are const_expr, but they don't have a const_expr in the title, so they don't appear in this list. And you can think of const_expr as enabling programming that shifted to compile time without having to express it as, okay, I need a static data member of a template, and then I need to grab its double colon value. That was always possible, even in CS+98, but it was really difficult. You really only saw that sort of programming in very template-heavy libraries like Boost and the STL. Now it's a lot easier. You just write const_expr, you obey a certain set of rules, and now you can get compile time programming. So here I've listed some of the papers we've implemented. There were 2 papers that const_exprized the algorithm header, and another one, const_expr numeric algorithms, also implemented by Nirki, that applied const_expr to accumulate and JSON difference and all the other algorithms that are hiding in the numeric header. But there's even more. There's been more complex applied to, more const_expr applied to complex. That needed const_expr bitcast, so all these pieces are fitting together. A very important feature is constant evaluated, which is really a compiler feature for MSVC that was implemented by our compiler dev, Jennifer Yao, and with a very small library wrapper on top. And that allows a const_expr function to sense whether it's actually being invoked for compile time evaluation or if it's just being called at runtime. That's what the standard refers to as manifestly constant evaluated or not. And so that is actually responsible for a lot of the const_expr stuff that we're doing whenever we want to do a cool optimization at runtime, like calling memset or memcomp. Is constant evaluated lets us combine that runtime optimization with a fallback for compile time programming where we cannot call C runtime functions like memset and memcomp. There's even more const_expr coming in the future. My coworker Mia is working on that. We've got some library support that will power the const_expr string and const_expr vector features. So there I've linked the GitHub issues that are tracking that work. So I mentioned that const_expr has been steadily increasing in power, but it might seem strange and irrelevant to you if you're not primarily a template metaprogrammer and you've been working at compile time for years already. If you just write code that executes at runtime, you might be wondering, well, why would I ever use const_expr? Why do I need to run code on my machine? I don't care about any of those features. But you probably have used lookup tables at some point. They're very common. And const_expr, especially with the new algorithms that have been added in CS20, is directly relevant to this. So if you have a lookup table, you can express that in lots of ways. One of the simplest ways in CS+ is just to say, I'm going to have a std map. I'm going to insert some key value pairs, and then I can just look them up by key. But if you think about what that's doing at runtime, that's going to be allocating memory for each individual node. And then lookups are going to be logarithmic time. They're going to hop through the pointers in this balanced tree. And that is not necessarily the most efficient thing. And yeah, you could use a hash table, unordered map, or another data structure like that, but you're still allocating nodes. And it's going to consume a lot of space, even if it is relatively efficient in time. So if you simply have an array, whether a built-in array or a std array of pairs of keys and values, that is as efficient as you can possibly get. You can't do better in locality than just having all your elements be contiguous. And if the array is sorted, it can be very time efficient because you can just use one of the STL's binary search algorithms to find what you want. It'll be logarithmic time, like all binary searches. So a hash table may beat it in some cases, but due to the compactness of the array is very, very efficient. And now you can use const_expr algorithms to make this easier to maintain. So if you have a sorted array, if you during maintenance have a programmer, maybe not you, maybe somebody else, come in and add an entry that is not in sorted order, well, you've just broken your invariant, and that's bad. But now, instead of having like a runtime check in like your debug build that checks that the array is sorted, now you can just say static assert is sorted my array, and if the invariant is broken during maintenance, your program will fail to compile, which is great. You'll never potentially ship that bug to your customers. And if you write a little more elaborate code, you can even make it so that you can add entries in any old order you want, and you can get a context per sort provided by the standard library to actually just sort your array as you build your program. You don't need a separate step. You don't need to run a script or something and generate a header that's picked up by the rest of your build. Context per can just do that as you compile your program, and then it all vanishes as far as runtime is concerned. So let's look at an example here. This is derived from one of our tools in the repo that scans our files and looks for things like trailing white space, overly long lines, and will trigger a check in our continuous integration system. But we want to skip files like DLLs, EXEs, object files that are just binary. So the way that we do this is we have a static context per array of string views. And string views have context per constructors that can be compared at compile time, unlike stood strings before the context per string feature. So here I'm also using class template argument deduction to avoid having to say how many string views there are in this stood array. I've got my list of skipped extensions there, which I have ensured as I program this, that I put them in sorted order. But I want to make sure that as this is maintained in the future, that invariant is preserved. So I can simply say static assert is sorted and give it that skipped extensions array. And if that succeeds, then there's no code executed at runtime to verify that it's sorted. It all happens at build time. Now here, just for clarity and to show off another feature, I'm using ranges is sorted, which is also available in context per compile time. That's implemented by my coworker Casey, who's been adding a whole bunch of ranges, algorithms and views and adapters to the library. But the original classic stood as sorted is also context per. You just have to pass it separate begin and end iterators. So after I verified that the array is sorted, then I can use an ordinary runtime binary search to see whether a specific extension is in the array. Here I just want a yes or no answer, so I can use stood binary search or ranges binary search here instead of lower bound or equal range, which I would need to find an element and see what it contains. So this is a hybrid of compile time and runtime programming as well. Okay, so let's switch gears a little and let's talk about what if you have a container and you have elements in it that you don't want anymore. This can happen for lots of reasons. Maybe you're building up, a list, and then the user decides that they want to erase, elements from it. Maybe you programming a game and you've got enemies in a list or a vector, and their hit points fall to 0 and they need to be removed. Any case where you need to cull undesired elements, how do you get rid of them from a container? Well, in previous standards, this was actually a surprisingly tricky problem. And the answer before CS+20 actually depended on the specific container you were working with. So if you had a vector-like container, and here vector-like means vector, deck, or string, you needed to use the erase remove idiom that books like Scott Meyer's Effective STL have been talking about for decades. And that's a very strange bit of code that you would never guess would be needed if you weren't specifically told about it. But if you have a list-like container, and here I'm referring to stood list and stood forward list, there are actually member functions called, strangely, remove and remove if that will erase elements. And for forward list, that's very important because it turns out to be really obnoxious to write by hand. For stood list, that's an interesting case because although you can use the erase remove idiom with a stood list, the remove and remove if member functions will just directly unlink nodes, which can be more efficient and require less from the elements. And if you have an associative container, whether ordered or unordered, so this is the map, multi-map, set, multi-set, unordered map, and so forth family, you don't get either of those approaches. You can't erase or remove because you can't assign keys in such a container, and there are no remove and remove if member functions. Instead, you have to write a handwritten loop that iterates over every element in the container and then uses the erase iter member function to snip out nodes that you don't want. But this is incredibly hazardous. So here I have a list of all the ways that it can go wrong. The first is if you just call the remove if non-member function and then don't do anything with the return value, that's a bug, because a remove if, despite the name, does not remove elements as a user would ordinarily expect. Instead, it compactifies the good elements at the beginning of the range and leaves the end of the range as unspecified garbage. Nowadays, it's typically moved from garbage. And you need to call the erase member function to get rid of that garbage at the end of the container, because the non-member algorithm cannot affect the size of the container. So this used to be a silent bug. Now we'll at least catch it thanks to the no discard feature that we've applied to over 3,000 functions in the STL. But it's still possible to get wrong. So the second bullet point there shows you can still write erase remove and get it wrong. If you write v erase remove if v begin v end pred, then that's actually a bug. And it's a very subtle bug, because if you look at that call, you're calling the single iterator form of v-erase, and that will erase a single element from the sequence and then shift the remaining elements backwards to fill the hole that's left. That is not what you want. You want to call the two iterator form of container erase to erase a range of elements beginning where the remove if returns an iterator all the way to the end of your vector. So you actually need a comma v end at the end there to get that correct. And this is very scary, because if you forget to say comma v dot end, it will compile and it will run, and some of the time it will actually work, because if you remove a single element, it ends up doing the correct thing. But if you end up trying to remove multiple elements, then you've corrupted your state. It's possible to get it right, but slow. So I've seen people write the loop to erase individual elements, but if you apply that to a vector, every time you erase one element, you've got to shift back the remaining elements, and that is classic quadratic time. And that's the sort of thing that'll seem fine when you test it with 10 elements, and it's going to fall over in production when you've got 10,000. So many other ways to get it wrong. If you've got the handwritten loop working in a map container, I've seen people invalidate the iterator that they're standing on before hopping to the next one. Or if you get your timing of increments wrong, you can skip elements, and that's very pernicious, because sometimes you'll be skipping elements that you wanted to keep anyways. But if you skip an element you wanted to remove, you've corrupted your state. And you've left elements that you really wanted to get rid of. So this is problematic. Why is something that is should be so easy so difficult? In CS plus 20, there's a feature, uniform container erasure, that I had originally proposed for the library fundamental STS, and then was later moved into the standard library. This took the form of a pair of papers that were implemented by our contributor Superwig. So here I've got an example. If I have a vector of string, and just fill it with the names of some animals, then I decide, okay, I don't want any animals whose length is greater than 3 characters. So I can express that in the form of a function, a lambda. Here I've got a lambda called pred. All I need to do is call std erase if and give it my vector and give it my predicate, and it will erase all the elements that satisfy that predicate. So here, bear and lion are length 4, greater than 3. Those will be erased, and I'll be left with just dog, cat, ox, dog there. I can also say, okay, I've got a specific value I want to get rid of. So instead of giving a predicate, I can just give it a value. I can just say erase all occurrences of dog. And here, it doesn't need to be the same type as the elements of my container. Here I have a vector of std string, but I can give it a classic C string. In this case, it'll be an array that decays to consecure star. And I can erase anything that's comparable to my elements with equality. So if I erase the dogs, then I'm going to be left with just 2 elements, cat and ox, that have survived those 2 erasures. So this is simple. and it is uniform. It works with all of the containers. There's one twist with the associative containers where only a race if is provided to avoid confusion. There's a bonus slide explaining that. But in no case is it going to compile and then accidentally do quadratic behavior, or compile but not erase all the elements you want. So that's the uniform container erasure feature in CS+20. Now let's switch gears entirely. Let's talk about multi-threading. So multi-threading has been a recurring theme of CS+, in CS+11 and beyond. And I hear in later standards, we'll be getting even more multi-threading, like executors and things like that. So one of the things that was added in CS+20 is called atomic ref. And if you've heard of atomic, then this atomic ref might seem strange, like why do we need yet another atomic type? And it actually ends up being similar but different to std atomic. So the way that I think of it is std atomic bundles together two things. A std atomic of T provides both storage for that T somewhere within its representation, and it controls atomic access. So you have to say .load, .store, .compare exchange weak, or use the couple of implicit conversions for assignments and loading, storing. And it's not going to let you directly manipulate that T. Atomic ref is different. It separates this by saying, okay, I will control the atomic access, but I don't own the T. The T is somewhere external, and I'm just a reference to it. This is kind of like reference wrapper that stores a pointer, but otherwise behaves like a reference. Atomic ref essentially stores a pointer, but otherwise behaves like an atomic. So the paper that proposed the feature P19R8 explains a couple scenarios, and my coworker Billy O'Neill explained another one to me. Those are listed here. So the reasons why you might want to use this: imagine that you have a program with a couple parts that occur separately in time. So at first, your program operates on some data structure in a single-threaded way. A common theme is like, I got to initialize it, or I'm going to load it from disk or something. And then later, you have another part of the program that operates on it in a multi-threaded, highly concurrent way. So if you make the whole thing atomic, you would be paying unnecessary costs. Atomic increments, atomic interlocked exchanges, or whatever your platform has, that are typically more expensive than plain old single-threaded operations. Having to pay that during the single-threaded phase of your code, where you don't get parallelism, so you really care about performance, that is undesirable. And yet that's a cost that std atomic would have forced you to pay. With atomic ref, you can say, okay, I'm going to use ordinary plain old T objects during the single-threaded part of my program, and then when it comes time to do multi-threaded things, I'm going to construct atomic refs and use them for the atomic access. Somewhat similarly, the paper P19R8 talks about programs that have non-conflicting and conflicting parts. So if you imagine like you've got a large array in memory, you can have parallel access to its elements without any sort of atomic access or mutexes, as long as each access is to a distinct element. In that case, the access is non-conflicting. So even if you have, a million elements in memory and you've got, 1,000 threads or whatever working on it, as long as they don't work on the same element simultaneously, you're okay. And later on, if you have part of your program that does need multiple threads, modifying a single element, at that point, you want atomicity. So that's another scenario for atomic ref. And then the third one is if you're working with a data structure that you can't invasively modify, like a C struct from external library code, and yet sometimes you want to update its members atomically, that's a use case for atomic ref. But aside from that distinction of, what do they store, they really have extremely similar interfaces aside from initialization. So it still provides all the advantages of std atomic. It's going to wrap up whatever special intrinsics or compiler magic is necessary to provide these atomic operations. And all the new features that atomic has recently gained, like wait, notify, notify all, those are supported equally by atomic and atomic ref. So this feature was implemented over the course of several months by our contributor, Alex Guteniev. It was quite a large PR. So I encourage you to check it out, see what's involved in implementing this feature. So this is one of those features that's really hard to present in like a single slide. Usually you would see it in the context of a much larger program that's doing interesting work in a multi-threaded way. In this case, I managed to condense it down to a single page of code, but it is extremely artificial and almost completely unrealistic. It does capture what I wanted to show, though. So here, I start off with an int, and I'm going to initialize it to some arbitrary value 500. Then the next line shows that this is just an int, so I can use ordinary operations on it. I can increment it by another 500. So that sort of turquoise line, that's just an ordinary read and write to that int. So now its value is 1,000. So that, in this artificial example, is the single-threaded part of my program. And then I decide, okay, I need to start doing concurrent modification of this because I'm going to do some, really complicated logic. So here I begin a new scope, and then I construct an atomic ref, also using class template arbitrary deduction. This is really an atomic ref of int. I'm going to call it atom. And so now this is going to control all access to I. And I should not directly modify I at this point. The standard says, hey, everything needs to go through the atomic ref now. So I can spin up a couple of threads that are going to compare exchange this value, and they're going to try to increment it, in this case, by 10 a bunch of times and by 1 a bunch of other times. And then I'm going to wait for those threads to join and destroy the atomic ref. So that concludes the multi-threaded part of my program. And now I can go back to using ordinary reads and writes. In this case, I'm just going to have an ordinary read. I'm going to print out the value of I. And at this point, I've arranged for there to be enough, increments by 10 and 1, that it's now the value 1729. So this shows how atomic ref can be used, but you have to sort of imagine it being used in a larger program. So I've heard that this is one of the most requested features for multi-threaded atomic programming. So hopefully that will be useful in your coding. So the last feature I want to talk about today is std span. This is a feature that was proposed by Microsoft. It grew out of our guideline support library, and now is available in standard form. So you've probably heard about span, but you may not know how to think about it or what scenarios you would want to use it. That's common when some new feature is released. It's like, okay, I've lived all the way up to CS+17 without this feature. What is std span doing for me? So the way that I like to think about std span is that it's like a pointer length pair, but better. So if you have a span of int, that says, I don't own these ints. These ints live somewhere else. They could be in a built-in array, a vector, anything that's contiguous. And I'm simply going to view them. This is much like a string view in CS+17, except that span works with arbitrary elements, not just character types. And span can be used to modify through to the elements, where string view insists on being read-only. So why would you want to use a std span? The reason is because of all of the library machinery that we've added to it. Then, library machinery can be complicated, but it's good complexity when it prevents you from writing incorrect code. So span has a lot of attention paid to its implicit construction. So you can construct it from contiguous things, contiguous ranges, like arrays and vectors, but you cannot construct it from things that aren't contiguous. We'll see an example of that later. And because span is a type in the type system, it's declaring up front that you don't own whatever is being accessed. It just says, I just want to view it. Maybe I want to modify the elements, but I don't control its lifetime. So I'm not going to try to delete some pointer that's given to me. I'm not going to try to free it. And it also avoids all the other hazards of pointers. Like, you can't accidentally add something to a span the way that you can accidentally add something to a pointer and adjust it through pointer arithmetic. And span also prevents other things that pointers would happily allow to compile. Span allows you to add consonants in its conversion, but it does not allow you to modify or traverse inheritance hierarchies. So if you have a derived star, you can implicitly convert that up to a base star. That's how inheritance works. But if you have a pointer to an array of derived objects, you do not want to convert that to a pointer to base and treat that as an array of base objects. That would be bad. Yet plain old pointers in the type system do that. Span does not. It detects, whoa, I'm only willing to add const here. I'm not willing to do derived to base. That needs an interesting bit of metaprogramming, and we've handled that in span. The other thing that confuses people about span is that it has shallow const. Now, it is true that other types in the STL obey deep const, but span is like a pointer length pair, and pointers are shallow const. So depending on where you put the const in the span, that controls, can I modify the elements? Can I modify the span itself? In this respect, span is very much like shared putter and unique putter, which are also shallow const, except that it has none of the ownership semantics of those types. So the one implementation specific note I wanted to mention is that our implementation of stdspan performs bounds checks in debug mode only, much like our std_vector. So in release mode, you get maximum performance. We're not going to perform any bounds checking in span and release mode, but this is a different philosophy than the guidelines support library. If you use GSL span, which is still supported and in fact is being updated to follow the new CS+20 standard interface, that always performs bounds checking, which is better for security, but comes at a performance cost. So let's take a look at span being used. I had talked about its construction. So span was implemented over a few PRs as the committee continued to patch the proposal by our contributor Misko, who is attending CPCon. And here, if I've got some function, to maybe print out a bunch of ints, I can call that function print, and I'm just going to take a span of ints. And here I want to say, okay, I'm not going to modify the ints themselves, and for the duration of this function, I'm not interested in reassigning the span. So I can have a const span of const int, apply const on both levels. And note that this function is not a template. It's just an ordinary, non-template function that happens to take a span of int, but it's not itself generalized on what it's operating on. And yet, I can call this function print and give it either a built-in array of ints, I can give it a std array, I can give it a std_vector. And this is performing a limited form of type erasure. No dynamic memory allocation or anything like that. It's just saying, okay, I need to construct a span, and I'm being called with a built-in array, std_vector. I'm going to invoke the implicit constructor. And that constructor itself is templated, but it's just going to extract a pointer and a length and then ignore the rest of the type information because we don't need it anymore. And so this will print 1, 2, 3, 4, 5, 6, 7, 8, 9. But if I try to call this function print, taking a const span of const int, and if I try to give it something like a std_dec of int, this will not compile. And I'm going to get a desirable compiler error. In this case, Clang will say, this is not viable. No known conversion from this std_dec that you gave me to the const span of const int that the function print wants. This is Clang's way of saying the constructor has chosen not to participate in overload resolution. And so this is very interesting. It may not seem that way until you think about what's happening in the library. So in CS+98 all the way through CS+17, random access iterators were the strongest possible iterators. They have the most power. Pointers are random access iterators, but they're also non-contiguous random access iterators like std_dec. I chose that specifically as an example. std_dec, if you've ever heard about its representation, it provides random access, but through a complicated representation that's a bunch of chunks of elements that provide some level of locality and yet are referenced by a map of pointers to those chunks. And that map is really just like a vector of pointers. It's not like a std map in most implementations. So dec provides random access, but the elements are not completely stored contiguously. So that means that although you can give dec iterators to algorithms that want random access iterators like std_sort, you cannot use dec iterators anywhere where contiguity is required. And so span cares about this. Fortunately, CS+20 ranges now provide a contiguous iterator concept and contiguous range concept. And now span and other types can use this to allow vectors, arrays, built-in arrays, and prohibit things that aren't quite strong enough like dec. And this is in a completely extensible way. So if you have a custom container, whether your own code or a third-party library that satisfies the contiguous range concept, you can give it to a stdspan. Stdspan doesn't need to know anything about that container as long as it supports the necessary interface .data and .size. Or I think non-member data, non-member size. And there are so many more features that we have added over the past year. I couldn't possibly talk about them all. but I do have a brief list of, and this is certainly not exhaustive, all the features we've added. We've got more atomic things. We've got atomic smart pointers that replace functions, individual functions that are quite horrible for correctness. These types, atomic shared pointer, atomic weak pointer, are type safe. That was implemented by our contributor, Adam Bussier. We've got a whole header called bit that provides sort of 3 categories of functions: a const expr compatible bitcast. You can rotate bits, count how many bits are set, do things like, is this a power of 2? Get me the ceiling power of 2, the floor power of 2. This was implemented over several PRs by my coworker Charlie, and then enhanced by our contributors, fixing issues with the intrinsics that we were calling. We have Make Shared for Arrays, which is a collaboration between our contributor Adam Bussier and our intern Gianni, who provided the testing. And this implements the optimization of allocating, in this case, an array with the shared pointer reference count control block that otherwise cannot be implemented by ordinary user code. There's another feature, midpoint and linear interpolation. And this was another collaborative effort. It was started by our former intern Paolo and my coworker Billy, and then it was completed by our contributor Statement Reply. There were a whole bunch of edge cases involving infinities and nans that were very tricky to deal with, and Statement Reply was able to comprehensively analyze those cases. So if you need functions like that in your programming, and you care about correctness even in extreme edge cases, those are now available in CSS20. And also in the sort of mathematical domain, if you just want constants like pi or e, now there are variable templates that express that in the std numbers namespace. The numbers header was added by our contributor Superwig, and it provides not just those, but also things like, I think, inverse square root of 2, square root of 3, things like that. There's a full list of the features we've implemented on our changelog. So let's now talk about how we've implemented these features on GitHub. I'd mentioned that we are a proprietary library that has switched to using GitHub for all of our development. And so that means not just the code, but also our issue tracking, our pull requests, our status tracking. We're migrating it all to GitHub. So the code, we used a linear history model. We enforced that all commits to the default branch are squashes. So we intend for it to be very easy to follow our history. It's just a single linear chain of commits. We are working in a couple of feature branches for large features, but we intend for those to be relatively short-lived. Once we finish features like spaceship and format, we'll merge them, squash them into the default branch, and then those feature branches will go away. They'll just be used to create the initial PRs. And for the issue tracking, we're not just using that for bugs. One of the important things we're doing is we're also using it to track the features that we're implementing. We have labels CXX20 for every top-level feature we're working on, and LWG for every library working group issue resolution, which are bug fixes applied to the standard, in addition to labels for bug, performance issue, throughput issue, documentation, so forth. And all these issues get resolved through pull requests. I'll show you how that is done in a bit. We've got the beginnings of testing with continuous integration. So we're using Azure pipelines to spin up Azure virtual machine scale sets that have their VMs that have Visual Studio installed, and Clang and Python. They run our test suite that was developed by my coworker Curtis. And then they also ensure that code in our repo is formatted with Clang format. We started using this back in VS 2019 16.0, and now we have automated detection that all files follow this. And this is a massive time saver. We love Clang format because it frees us from having to worry about, okay, where exactly did we put the brace? Is all the indentation right? We have the rules written down in our repo and enforced by the tool, which is a huge time saver for both development and review. We're using GitHub's other features like projects. This was actually encouraged by our contributor, Misko. We started using a project for code review. I'll show you how that works, in addition to tracking CS+20 features and the feature branches that we're working on. We have projects for those as well. We're using GitHub's wiki to be able to present an STL change log that's continuously updated. Every time we merge a PR, we now go update that change log. This is a vast advancement over our previous mechanism of whenever we commit something, one of the developers will send a mail to themselves. And then later on, when a release happens, we'll go through that mail and write up all of the features that we've accumulated. And we've even started sharing our status chart, which I shared a screenshot of earlier. This is now available through GitHub pages, and we can just query GitHub's issue database whenever we want programmatically using GraphQL and generate that highly detailed status chart to understand, okay, what progress are we making on features, how much are we merging PRs, are PRs accumulating, and that we need to start reviewing. So the code, I've got the URL to the repo there. Often when you see a directory listing, you don't know where to start. So I encourage you to look at STL Inc. And that's where all the headers are, like vector, charconv, ranges. That's where all the fun happens. But you can also look at STL source. Oftentimes source is where people initially go. Why wouldn't I want to look at the sources? In this case, it's our separately compiled sources, which are things like IO streams, file system, and threading. It's actually a small portion of the STL. And it tends to be a little more complicated because we have to work with the platform API and care about DLL exporting and things like that. Our build system is powered with CMake and Ninja. We're writing this from scratch and replacing our existing MS Build powered build system that nobody really understands. CMake Ninja is wonderful. It's so fast, easy to extend. And we use VC package as a submodule to build boost math because we use that to implement the special math feature. We've got our test suite in there. Our own test suite is called unimaginatively teststud. We've got a libcxx directory containing some support files for libcs+'s test suite. And then we've got a legacy test suite as well. And I talked about the history and the feature branches. So the issues, I had mentioned the various labels that we're using. Here I've got examples of some issues that are interesting to look at. We file one issue for every remaining feature to be implemented. And these exist as of CPCon 2019, all the work that was outstanding back then. We did not go even further back and retroactively file features for stuff we had already done. That would have been unnecessary work. But for all the features that were outstanding as of 1 year ago, there's an issue tracking that. So is open label CXX20 will show you all of our remaining work. And we group together papers in the standard that add new features, followed by any papers that have patched those features because they don't represent net new work. They just represent things that we have to remember as we implement the feature. I had mentioned our LWG and other bugs that we're tracking. We're porting those from all of the various other sources that we have accumulated bugs, but we still support people filing bugs through developer community or the IDEs report a problem. It's just that GitHub will now become the central place to view all issues that have been reported against the STL. And we've got a label vnext that tracks our upcoming project to overhaul the STL and break binary compatibility. So here's an example of one of those CXX20 issues. This tracks the context per string feature that Mia is working on that I mentioned. So these issues tend to be relatively minimal. We will link to the paper. So you can just click on that. That'll take you to the WG21 website. We'll mention if it's controlled or if it's tracked by a feature test macro, if there are any patch papers or LWG issues that affect it. Then we can just mention this issue whenever a PR comes up or if other issues depend on it. And track it in our various projects, our milestones. So this is trying to present our status in a very legible, understandable manner. So the pull requests that are the flip side of issues, here I've got a few examples of interesting pull requests. We've got the changelog entry fixed a 43-year-old bug by implementing a 40-year-old fix. That was very fun because it involved an incorrect paper that Donald Knuth co-authored. So this pull request is an interesting example of a comprehensive explanation of the bug, what went into the fix, ABI concerns, how to test it. We've got a randomized test in there. And this was a wonderful example of working in the open on GitHub, because when we filed this issue, others provided, our contributors provided more information. They linked to papers in the CS literature that we hadn't heard of that provide other algorithms that we can use to improve performance in the future. I've linked the span PR, which is currently the longest PR in terms of the number of comments we accumulated. This one started, it was contributed by Misko before we had our test suite online. So we also had to add tests to the PR and then deal with all of the papers that patched it. So that's a very lengthy, very interesting PR to follow. And then a more recent one, statement reply had fixed longstanding issues in our OStream floating point printing. And this was an interesting example because to fix it, we had to avoid breaking ABI. And it was wonderful to get this PR because we didn't know how to fix it immediately without preserving ABI. And statement reply figured out how to do that. So each of these PRs is a collaboration between our contributors and the STL maintainer team. We've got a policy that 2 maintainers need to review and sign off on every PR. This keeps code at our always ready to ship level of quality and ensures that the maintainers understand what's happening in the repo, so we can write further features in that area and understand what's going on when bugs appear. So when we review code, our library is a little bit different from other code bases. We're controlled by the standard. So the standard does the design work for us. It specifies the preconditions of what users are allowed to give us, both in values and in types. And it has very well specified post conditions of, okay, the state of the program needs to be exactly this when you're done. And the requirements that we have to meet are very strict. And this is not just because, okay, the standard's strict. It's because we have to deal with all of the users of the standard library, and our correctness and performance requirements are essentially the maximum of any of our users. So we're not quite, space shuttle levels of correctness requirement, but it's pretty stringent. The standard library has been around for decades. It will be around for decades. So it is a perpetual code base, and it needs to be constantly evolving with all the changes to the standard that are happening. So by intensively reviewing the code, we can avoid adding new bugs to new features, and we can avoid regressing existing features. And that way we can stay focused on moving the code base forward rather than having to go fix up a bunch of things. And this intensive review also ensures that the code base remains highly consistent. If you look at our code, it mostly looks like it was written by a single person. And this has a lot of benefits. It means that as you write a new feature, you can look at existing features for precedent and follow what they're doing. Now, you never want to mindlessly copy paste something, but if you follow its precedent with your eyes open, you can end up writing code that correctly handles unusual cases like, oh, okay, what if I've got a container that sets the propagate on container copy assignment type trait to true? Do I correctly handle that? And if you follow existing code in Vector or any of the other containers that all looks generally the same, your new code will end up doing the right thing. And if you have to do something unusual, it will stand out during code reviews. Oh, okay, this is tricky. I need something that's a little bit different than the usual. So this is what the code review flow looks like on GitHub. We've got a series of columns where PRs migrate from work in progress to initial review to final review to ready to merge as it gets reviewed or sent back for rework by requesting changes. And here's a screenshot of that status chart. This shows we've got 3 graphs in there. This is the third one. This shows the number of PRs merged per month since we went open source. And so the pace has been increasing. In the month of August, we managed to merge over 70 PRs in a single month. And hopefully that will continue increasing, although it'll be a little bit lower due to CPCon this year. So that is the end of 1 year of development on GitHub. We're starting our 2nd year. This will be the year that we finish CS+20, hopefully this calendar year. And we are looking forward to working with the community. So here I've got a list of links, links to our repository, to the changelog I mentioned, to the status chart. You can reach all this from the repository itself, and a link to the current working paper for CS+20 that's available on the W21 website. So I've got about 6 minutes to answer questions. Let us see what is in the Q&A. And if you have more questions, our GitHub discussions tab is open, and we've set up a Discord server. Look at our README in the repo that has a link there. Okay. So first question, why isn't constexpr implicitly added by the compiler to any function when suitable? Is there a downside to it? That is an excellent question. So the reason that const expr is not implicitly added is because it is not just I can use this at compile time. It is it's a guarantee that I will never do anything to this function that will prevent it from being eligible for const expr. I will never add things like runtime logging or a network request or a reinterpret cast. So const expr being automatically applied would be undesirable. When you mark something const expr, it is going to be a hopefully permanent guarantee, because if you mark something's const expr, people depend on it, and then you remove const expr, now you've just broken their code at compile time, and they may need to extensively rework their code. So that's why it has to be explicitly written. Okay, next question. Is erase if similar in complexity to calling remove if then erase? It is. In fact, it is implemented for the vector-like containers as remove if followed by erase. That's mandated as if by the standard, and in fact, that's what implementations will do. So the erase if functions are all linear time, regardless of whether they choose the erase remove idiom, the remove and remove if member functions, or the handwritten erase iter loop. They're all linear time. Next question. What's the next big CS+ thing Microsoft is going to open source? I cannot talk about future plans with any sort of specificity. We are looking at open sourcing the VC runtime and VC startup libraries that are directly underneath the STL. No promises, no guarantees yet, but that is something we're looking at. Next question. What is the motivation for people contributing to your GitHub project? Is there any incentive to do so, or are these people just lovely enthusiasts? I believe that they're lovely enthusiasts. I suppose the incentive is that you get to see your work shipped to over 1 million user programmers and make C++ a better place. I can't comment on the other motivations of our contributors, but I imagine that that's the case. Let's see, next question. Does the array have to be static for ranges is sorted to work? It needs to be, if you're going to use the const expr is sorted, the array needs to be const expr, but it does not need to be static const expr. So it's okay to have a function local const expr array, and then use static assert is sorted or static assert ranges is sorted. Okay, next question. What were the downsides of moving to open source? So it's a one-time time cost to get everything polished up, to physically move things to GitHub, get the repo set up, and there's an ongoing cost to replicate changes between the GitHub repo, which is where we're doing development, and the MSVC internal Git repo, which is where the product is physically built and then added to the VS installer. And then there's the ongoing time commitment of needing to review PRs, which initially was a big change for us. And now we've got it humming pretty smoothly. So I'd say those are the downsides, and those are definitely things we absolutely expected going in. Aside from that, it has been remarkably great. Next question, is const expr available on parallel algorithms? No, none of the parallel algorithms taking execution policies are marked as const expr in C++ 20. That may change in the future. I don't know exactly when. I would imagine that the implementation would be like, oh, okay, you can call parallel algorithm const expr, and then it'll just do something serial at compile time because you can't tell the difference. But I don't know if the committee is planning on doing that. Certainly not. There's no concrete proposal yet. Next type, why is passing by value faster for small types like span? When do we decide a type is not small enough? Excellent observation. I did pass a span by value. That's because it's just a pointer length pair, and the idea was, okay, the compiler should be able to handle that efficiently, hopefully pass it in registers or something. Generally, our criteria is if you are the size of a built-in type, like an int or pointer size type, or up to 2 of them, and plain old data, so you're not going to do any dynamic allocations. That's small enough to pass by value. But if you're larger than that, like 3 pointers large, or if you have any sort of complicated logic in your copying, assigning, then you should probably be passed by reference. Span is one of the few library types that I would pass by value. There also I would pass like maybe a pair int, but that's about it. And final question, thoughts on the new code development dynamic after open sourcing? So yeah, we are building a new dynamic here where we're collaborating with developers and trying to plan things out. I'd say the biggest challenge is scheduling things, because right now we have a finite capacity to digest PR, so we're prioritizing CS+20 features, but we don't want to completely shut ourselves off from bugs and enhancements and other things like that. So I would say communicating our plans without overpromising, that is one of the things we'll be working on in the next year. So that's our time limit. If you have further questions, feel free to submit them on our discussions tab, Discord server, or send me an email. Also, we'll be here at the conference, so drop by our booth. Thanks.